Hello everyone, Call for Zero. In this video, I'm on Ray's channel talking about level Earth and upward vector, presenting some clips of various tests, and talking theory afterwards. So let us begin.
Earth is not flat.
Correct.
Okay.
So we're introducing boxes that provide factual information at the top of results that have shown themselves to turn up a lot of information that is counterfactual, such as searching for the Earth is flat on YouTube, where you see a lot of...
Your response is to put a box saying, nope, the Earth is not flat.
Okay, Mr. Dooch and Ms. Downs have their ideas pretty much set in stone and went to make sure nobody gets polluted with real information. We can see from this high-altitude balloon over 100,000 feet, it's level. The next video are wind fans offshore. They are spaced approximately a half mile from each other heading out. This video represents what we should see from the beach regarding Earth curve ocean blockage. A zoom camera shows the bases of the fans in the distance. This is the first inertia test. We have a socket on a ruler being dropped that all drops equally, but one end is touching Earth. It appears to be pushed up, breaking the socket free from the high end of the stick. Let's look at this again. Shouldn't it all fall together? Isn't the pull of gravity equal on all the parts? Is something pushing up on that right end of the ruler, breaking the socket free? Here's a plank with a heavy sinker. Same idea. It all goes down together until it's attached to Earth, and then the right side is pushed up, breaking the heavy weight free. And now here's a light object, a cork. Same thing, the right end of the stick is being pushed up. All this is done with a $5 driveway experiment. You don't need vacuum chambers or hypothetical space. Okay, here's a basic inertia test. When force is applied on one end of the stick, the other end reacts and moves in the opposite direction. A force creating motion. Same idea here. All right, here's a cup with fluid. Air is injected into the cup, forming bubbles, and in free fall, the buoyancy density idea is not working. It just simply meets the rising Earth. There's no density causation for a bubble moving up here. It's not moving. There's nothing to push the bubble up. The final test is from William. Here we go.
Recreating density and buoyancy in 3 different vectors utilizing motion of a contained reference frame. In the first experiment, I'll be using a container with water, a red ping pong ball, and a steel ball. The ping pong ball and the steel ball will always displace relative to the direction of the force that's applied. For example, when I accelerate the container to the right, the container pushes the water in the same direction, creating a pressure gradient. The water is then able to push anything that's less dense, like the ping pong ball, in that same direction. That is what we would call buoyancy. However, the water is not dense enough to push the steel ball like the ping pong ball, so the steel ball remains in the same position. The steel ball only appears to move in the opposite direction of the buoyant force because the camera is also moving with the container. The ping pong ball has true motion and the steel ball has apparent motion. The same principles apply when I accelerate in any other direction. In the second experiment, I'll be using a tube with water, an air bubble, and a steel ball. To accelerate the container down, I will be using a resistance band. As you can see, when connected to the earth, we can experience a force creating density and buoyancy. The air bubble is being pushed up, and the steel ball appears to move down in the opposite direction of the buoyant force. You can also see the air bubble is flattened where the force is being applied. However, when I release the container into freefall, density and buoyancy completely vanish. The air bubble is no longer being pushed up and turns into a sphere, showing that there isn't a force present in freefall. When I actually accelerate the container down, we can see density and buoyancy invert. The air bubble is being pushed down and the steel ball appears to move up. Not only does acceleration require a force, acceleration will always cause displacement of solids, liquids, and gas, proving that objects don't accelerate down in freefall. In this video, I'll be showing that flames always follow the direction of the force. Flames are less dense than air, so depending on the direction of the force pushing on the air, that will also determine what direction the flames get pushed. For example, when I have a flame in a container with air surrounding it, as soon as I apply a force to the right, there's a greater compression of air to the left that is then able to push anything that's less dense, like the flame, in the same direction as the force. When I apply a force to the left, the greater compression of air to the right is then able to push the flame to the left. This can be demonstrated and repeated 100% of the time. The flame will always get pushed in the same direction as the force. When I actually apply a force down, we can see the greater compression of air switch to the top of the container, pushing the flame down, showing that there is a force present. However, when I release the container into freefall, there is no compression of air in the container, so the flame is not being pushed in any direction and thus turns into a sphere, showing that there isn't a force present. The compression of air in the container is only present when connected to the earth, pushing the flame up, showing that the force of the earth is also up. You can't have acceleration without a force, and you can't have a force without any reaction of the flame.
Okay, that's the video presentation. An object attached to Earth continues upward with the entire system rising. And an object disconnected from Earth is rising but decelerating. It comes to what you could call a pause and then appears to accelerate downward. It's a slowing to a pause and then a reversal. I saw this in a video 3 or 4 months ago where a car was moving along at about 30 miles an hour. A ball was tossed out the back of it. The ball bounced a couple of times, decelerating, yet continuing to chase the car. Like the ball did not land and distance itself from the car, it chased the car that was already in motion because the ball was still in motion, decelerating. When we see, for example, an arrow fired straight up, it pauses, then returns down, and what appears to be acceleration. Then there are questions of contained system, air pressure, rate of rise of the upward vector system. My investigation shows you can look at various speeds of objects appearing to fall and get an idea of what's going on. I will list 3 examples. A skydiver laying prone with the chute not deployed will reach a maximum speed of 135 miles per hour. Whether it be a 500-foot jump or a 5,000-foot jump, the skydiver is going to max out at 135 miles per hour. If the same skydiver rotates and goes into a pin drop position, like a spear, the maximum speed is 165 miles per hour. The air, the ether we breathe, provides resistance. It maxes that second skydiver at 165 miles per hour. So when I got these first 2 numbers, I considered what would be the object that falls the very fastest, without external force, without being thrown, without being shot. So I looked up bowling ball. How fast? What's the maximum speed a bowling ball can attain? My early searches about this were 3 months ago and revealed 300 miles per hour. So in my mind, that's going to be the maximum speed any object will naturally appear to fall, 300 miles per hour. Interestingly, if you search bowling ball now, it doesn't give you that figure. It says, well, it could be 100 miles an hour, it could be 200 miles. It's like they changed it. They didn't want the information to be clean, but when I searched it, it was a clean 300 miles per hour. Taking the resistance of the atmosphere into account, I think it's pretty safe to say it would not reduce the speed 50%. It would have to be pretty thick to reduce the speed 50%, so let's say it reduces the speed 25%. This gives us a mile per hour number on upward vector of approximately 400. I'm not saying this is the speed, but just looking at the overall big picture, it kind of matches up. A few months ago, I considered mudflood theory and rising Earth with a figure of 400 miles per hour for the number. The whole system were rising at 400 or 500 miles per hour and it changed speed. It would be A, B, or C. It would be a very slow decel over about a minute's time, a moderate decel in 15 seconds, or a hard decel in 2 seconds. I think it's pretty safe to say if the system is rising over 300 miles per hour and it stops in 2 seconds, mud, water, any loose debris is going to be lifted 100 yards in the air perhaps. They would all rise. But your huge block cathedrals, large stone structures, pyramids, they could probably resist it. This brings into question the reason for building everything so strong and stout and heavy in the old world. Is it because they're aware they have to withstand a periodic reset? I don't know, but it's something to think about. I'll give you a few examples of cities across our level plain in their elevation, over 3,000 feet elevation. The abrupt stop, the local waters rising, 10 to 30 feet of mud along the edge of the buildings. Denver, 5,280 feet. Salt Lake City, 4,200 feet. Mexico City, 7,340 feet. The capital of Turkey, Ankara, 3,700 feet. These are some pretty high cities. Without even looking, we know there's going to be mud-flooded buildings there. Tides in the upward vector system are a brand new exploration that we're just starting to look into. Williams' theory is that a force is required to move the water. It just doesn't move on its own. So if you think of a pan, like a baking pan with an inch of water in it, you lift the pan, not precisely straight, there'll be a high level at one end and a low level at the other end. The middle, the pivot area, will be very minimally shifted. It'll be mostly the extremes that you'll notice it. So if we look at the flat Earth map, we have Alaska tides being the most extreme at 24 feet. And the tides off Vietnam, pretty significant, 4 meters. That's about 14, 15 feet. And here's a picture of Vietnam, the east coast of Vietnam. Darwin, North Australia, 19 feet. pretty significant. So it's looking like Alaska and Australia are our extremes, whereas the area between Jamaica and the Mediterranean have next to no tides. The Azores out in the middle of the Atlantic, nothing. Jamaica, almost nothing. Mediterranean, between 6 inches and a foot. Montego Bay, Jamaica, 1 foot. It's more food for thought. And like I said, it's data. We're just piecing together a big picture at this point. Thank you all for listening.